Record to the computer. So here we are, another week. This is mission 8, test for proportions. And as I sort of outlined in the course, essentially, we have, I like to divide sections into two different, foundational aspects. One part is the syntax and the code. How do you program your way through the course? And then the other part is conceptual. How do you understand and interpret and understand how you got the answers right, how you got them wrong, why it's one answer as opposed to another. And that's what I do in this review, is essentially go over some of what I see as the main concepts that are important for each homework assignment. So, and this is relevant both for the midterm, but also for the final exam, which covers both the midterm material and the final and the second half of the course. So, so I think what we'll do this week is, since, as I said, one of the students, as I was talking before I started recording, is what one of the students had a question about the last problem in this problem set. So we'll start with that, and then I'll sort of work my way forward, if you will. I'll probably start in each section. We'll see. But let's go to this last problem because the student had asked about this, and if one student has, I'm sure there are others. So question 30 reads thusly, and if you can see, if you look at this, my screen share, you can actually see, okay, here I have the question, and then you can see basically the format that you'll see for the problem set. You'll see that I just printed it out pretty recently, but I didn't even bother to answer it. But what's more important is, well, okay, you can get the answer right, you can get it wrong, but the relevant question is, how do you get there? So let's look at question 30. You can see that the correct answer is negative 3.92. But let's look at how we get to that answer. So the question 30 reads thusly: a famous sociologist approaches you and wants to know if the average age differs among people who view sociology as scientific or not. Now, keep in mind, this is a question that addresses some analyses of the data set. And this sociologist believes that older people might view sociology as less scientific than younger people, since the nature of sociological studies has changed over time. Using statistical software, in this case we've been emphasizing RStudio, conducted two-sided tests of the hypothesis that there is no difference in the average age among those who view sociology as scientific versus those who do not. What is the point estimate? Round your answer to 2 decimal places. Well, this is an interesting question, but to understand how do we get to the point estimate, keep in mind that we're, for this answer, as I have told some of you before, this actually deals with a t-test of a difference between 2 means. So it might be a little beguiling here, right? Because in the question we ask for the two-sided test of the hypothesis. Well, we don't really tell you what kind of test you're supposed to do, but if you look at the code in the problem set, it's actually, you'll see that it uses the t-test function. So if I can add some text here, this is the t-test function, right? And the question, might want to figure this out. What is the question asking? It's the question asks for a difference in 2 means by a categorical variable dividing sample into 2 groups. Right, so this is actually a revisit of the t-test of a difference in 2 means. So what we're asking you to do here is actually, when we talk about the estimate, we're actually asking you to think logically through the problem and figure out, well, what are the means of one group minus the mean of the other group? And that's going to be our point estimate. And that's essentially what we come to as the answer. So here, the null hypothesis, so the null here, or H naught, you can do an underscore, is equal to the population mean of scientific, right, who believe that scientific, and then minus mu, or I should say mu here. This mu is the population parameter for one group, and then the population parameter of age for those who think sociology is not scientific. And then all we're doing is we're going to then basically look at the output. If you look at the output, you'll see that the mean for among those participants in the poll, who said sociology was not who was scientific. What's their average age? Well, their mean age or average age is this, 44.72. And then you basically subtract the mean age of those who say sociology was not scientific, and that's 48.64. And that difference is equal to negative 3.92. Now, my answer is a little bit overloading this a little bit. I hear a little bit of background sound there. Just make sure, if you can double check to make sure that your own sound, your own microphone is turned off, just because I don't want that necessarily to be recorded unless you want that to be for posterity. That's okay too. All right, so that's our answer basically. Now, when I reviewed the code, and if you want to look at sort of further extensions of this code, you can actually see some of the other questions that we asked that were related to this that we did not include in the actual homework assignment, which had to do with what would the hypothesis be here? How do you interpret these in terms of H naught and HA? What is the point estimate? How do you conclude? What do you conclude at the alpha of 0.05? Just for fun, you actually conclude that there is a difference in the mean ages in the population among those who view sociology as scientific versus those who do not. So notably, you actually find that this difference is that that basically people who view sociology as scientific were considerably younger, about 4 years on average, and that's what we find. So I think the insight here is that don't always assume when you're answering a question, don't always assume that just because we're doing a homework assignment on proportions, that by definition we're actually going to request that you're going to do the same kind of analysis. That you should sometimes, keep your mind toward the question, the wording of the question. In this case, I think the insight is essentially to understand, first of all, what test is being done here, what is the logic of the homework assignment, what is the logic of the research question, and then also what are the terms here? What do we mean by point estimate? Well, the key term here is when we talk about point estimate. I'm going to change my annotation to a spotlight, so you should be able to see this. What is the point estimate here? The point estimate is the mean difference of one group minus the mean difference of the other group. I should say I want to interrupt myself though, because I just realized I did not finish that thought here, which is when I'm going to clear the wording here. Clear everything that I've written here, because I want to emphasize that H naught here actually is when the difference in the two group means are 0, or right. So mu of scientific minus mu for not scientific is equal to 0. And then the alternative hypothesis, H of A, you could say, is essentially when the two group means or proportions, but keep in mind we're talking about means here because we're talking about differences in age between those who view sociology as scientific versus those who do not, when the two group means are not equal to 0, right? So you could do a bang equals 0 here. Okay. Okay, so those are the two distinctions here that I wanted to make in terms of framing the hypothesis. Now, when we look at two differences in proportions, just keep in mind the H of naught and HA are just talking about the differences in the two proportion means. So if you look at the first, someone had asked, well, is there a reference to age here? Actually, we do see a reference to age. A famous sociologist approaches you and wants to know if the average age differs among people who view sociology as scientific or not. So when you look at the data set and you look at the variable here, you just want to be careful just to remind yourself, well, what kind of variable are we talking about? Well, if you're looking at the difference in two integer variables, and when you look at the data set, you can see that the age is in fact an integer. Logically it is, but not necessarily, right? It could be a categorical variable, right? We could look at, say, the proportion of people who view age above a certain group. But in fact, when you look at the data and you explore the data frame, just through the basic view function, for example, or just through the viewfinder, you'll see that age is actually an integer. There you go. So Okay. Thank you, Walter. Any other questions about that? Otherwise, I will continue. And actually, I think I'll start with the first part of the homework assignment, because that sort of drills down to proportions. And there is a point that I want to make regarding the first part of the homework assignment. The caveat, however, is you'll notice that there are about 30 questions here. I won't be able to address all of them probably with as much detail, precisely because notably, it'll take about 2 minutes per question. I want to make sure that I can address every concept. So I might not go over every question unless you ask for it. So question 1, we ask about, we talk about a sample of 30 adults, and we find that the proportion who support an increase in government funding of scientific projects is p hat. So p hat, of course, is our sample estimate of the true population parameter of a proportion. And proportion is simply whether you not belong to one category or another. So the fact that we're using p hat in our annotation tells us that we're looking at a probability of something being true or not true, or an opinion expressed in one way versus another way. And we know that, in other words, that when we're talking about a proportion, we're talking about sort of a crisp definition of how can you cut the sample into two groups based on their attitudes, their probability of endorsing an opinion, their probability of an outcome, something like that. It's almost always, it's a binary probability. So when we look at p hat, when we look at this annotation, if you see p hat equals 0.70, keep in mind that you're talking about the proportion here of the sample who endorse or expresses some attribute. So in the class lecture notes, I think when I was reviewing for this section, I think that it's referred to as pass-fail, sort of a pass-fail binary variable. So just keep in mind that that's what the p hat annotation represents. And it's, by definition, it's p hat. If you remember the notation from the course slides, the course module, the hat refers to a characteristic of the sample, as opposed to p, which references the population parameter. So just keep in mind that p hat equals 0.70 is by definition, by notation, a description of the sample. Now we want to say, we state the following. You want to make an inference about the proportion in the population conducting a one sample z-test. Check the success-failure condition. What do you conclude? So here's this new concept, success-failure condition. I'm going to flag you for this. What does this exactly mean? Well, the success-failure condition is, if I can scroll down, hold on for a second. Sorry for a second, I just need to close the door just so I don't want to lose you. I don't want to have too much background noise. The success-failure condition here suggests that a one sample z-test may not be valid in this case. Well, what exactly do we mean by the test failure condition? What does this mean? Well, the success failure condition is tested by using the sample proportion. And I think, if I'm not mistaken, yeah, I wrote in the answer before. So if you didn't get it right, and if you did get it right, actually, I did not get it right here, but even if you did, you should, I think we flag you for the answer. You can tell me if not, though. But in Canvas, if you don't get it right, as I have done, obviously I got the answer wrong because I did not fill it out. And you see that you want to check the sampling distribution. And we have to assume that the sampling distribution is approximately normal. But we have to first assume that the probability of NP is greater than 10, and N times the inverse of P is also greater than 10. And now we cannot absolutely know with certainty whether the success failure condition holds, because it is based on knowing the population proportion P, right? Remember that difference between P and P hat. However, we can still assess this assumption using the sample proportion P hat. Well, we know what P hat is, don't we? And this is the main rule I want to point out is that when it is less than 10, we have actual cause for concern. And now, how do we know what the value is? Well, you can basically figure this out by knowing that 30, our sample size, n, times 0.7 is 21, and 30 times its inverse is 9. So in other words, our first condition is met because our what we assume to be the population parameter, 0.7, because we can assume that based on our sample p hat. We're just going to assume that we know what p is based on our estimate using p hat. And then we are also giving you what n is. So if you want to write, when you're answering this question, just put in the margins, okay, I know what n is, I know what p is, based on the assumption. And then based on the assumptions of that we have a random sample of n equals 30, and then we're going to assume that p hat is our estimate of p. Then we can take 0.7 times our sample size, which is 0.7 times 30, and that's going to be 21. And so then we know that our first condition is met, but our second condition, which is 1 minus p, or 1 minus 0.7, which is 0.3 times 30, is actually equal to 9. So 1 minus 0.3, 30 times 0.3, as opposed to I guess 0.7 times 30. So 0.7 times 30. So the main point is that we cannot know the absolute certainty, but we should have concerns because the second condition is not true. Okay. So the main point I just want to point out is, the main point I want to make is that you want to check the success failure condition. That's when I want to flag and just let you know that you should probably look for this equation right here. Okay, so we extend this question and we ask for question 2, instead of a sample of 30 people, suppose we have a random sample of 50 adults, and you want to find the proportion who support an increase in government funding of scientific projects. P hat is still 0.70. You want to make an inference about the proportion found in your sample of 50 to the adult population. What is your point estimate for the population proportion? Well, it's pretty simple here. Remember that we were going to make the assumption that our population population parameter is going to equal p hat, and looks like we didn't write an answer there, but just remember that in this case, the point estimate is simply the sample proportion of 0.70. This is our best guess at the population proportion without additional information. So without additional information, you can safely assume that p hat will equal p in expectation. In fact, this is why we often talk about sample means or sample proportions as the expected value of our population parameter. You can hear that language when we talk about a lot of aspects of statistics. In fact, you might even hear some statisticians refer to the mean or the average as the expected value of something, of a particular variable. The main point is that in expectation, without any additional information, p hat is equal to p without any additional information, assuming that we have a sufficiently random sample of the population. And so that's question 2. Now we ask, using what you know from question 2, i.e., given that we know what the sample size is and what p is estimated to be, what is a 95% confidence interval? And just keep in mind here that it looks like we don't have an answer written here, so I want to make sure that you know this. So just keep in mind that the 95% confidence interval formula is p hat plus, so sometimes I'll do an underscore here. That's just to reference that if you look at sort of a p hat will sometimes, as opposed to this little expression, a little caret here, p hat, this would be sort of like a, I'm not sure how to even put it, but a different kind of formatting. If you see something like this, just keep in mind that p hat here is in reference to the annotation that we have before. So when I use the p hat annotation here, just sort of informally, just keep in mind that it's the same as you would when you look at, hold on for a second, when you scroll up and you look at this right here. So when I show that to you, just keep in mind that p hat's a little different. In any case, the 95% confidence interval, we often sometimes talk about it as the 95% CI here, is equal to our estimates, sample estimate of the proportion, or p hat, plus or minus, or so plus and minus 1.96 times our standard error. Well, look at that. Okay, well then all we have to do is figure out what the standard error is. Well, what's the standard, and why does this condition hold true? Well, because of that beautiful aspect of the normal distribution. You can basically figure out the mean of something, or the average of a particular variable, as long as it's sufficiently normal, and then add or subtract how much does the random sampling distribution of proportions vary on average, which is about 1.96, or 2 standard deviations of the proportions, or standard errors. And how do we estimate the standard error then? Well, the standard error, fortunately for us, we can estimate by, when we talk about proportions, by the information that we have on hand using with p hat, which is in essence the square root of essentially our numerator variables. So it's our p hat times its inverse, or I want to write this so it's not too complicated, but basically the square root of 0.7 times 0.3 divided by, let me put this numerator in parentheses, divided by our sample size of 50. And you take all that mess here, take this little ratio here. So you basically take the two sample proportions, the sample proportion and its inverse, and divide it by the sample size, and then take that whole mess, give it the square roots, because we're not dealing with variances. We want to know the standard error, which is the standard deviation of essentially estimated deviations. And the beauty of this with dealing with proportions is all we need are basically two pieces of information to estimate the 95% confidence interval. We need p hat, or the inverse of p hat, which is 1 minus p hat. And then we need to know the sample size. With those two pieces of information, you can pretty much estimate the standard error, as long as the two conditions are met regarding the first issue, the question that we addressed in question 1, which was the success-failure condition. As long as we meet the success-failure condition, yeah, we can estimate the 95% confidence interval this way. So what is the 95% confidence interval here? It's essentially, well, in expectation will be 57 to 83 for given our estimate. Okay. So if you have any other questions regarding this, I know we won't be able to address all the aspects, but I want to be somewhat judicious with our time. I think some of these questions are going to iterate around some of these very similar concepts, but just keep in memory how to estimate this 95% confidence interval, what the equation is, how to know that the sample proportion in expectation is equal to the population parameter p, as long as the success-failure condition holds, I should add. So using what you know from questions 2 and 3, what is the standard error approximately? Essentially, I already told you how to estimate the standard error. Should be around 0.06, and that's because I want to make sure that I give you that information correctly. Yeah, it's probably, actually, you might have this down to 0.0648, I think, if you're very persnickety. Now, just keep in mind, how do you estimate the standard error? I already told you. You take the p hat minus 1 minus p hat, multiply that, and divide that product by the sample size n, in this case 50. So you take 0.7 times 0.3 divided by 50, and then take that square root, and you're going to end up with 0.0648. Exactly, 0.064. There you go. and that'll round down to 0.06. So we know that the 95% confidence interval is between 0.7 and 0.83 approximately, and we're 95. So we can conclude that we're 95% confidence that the true population proportion is between the endpoints of our 95% confidence interval. Alternatively, we can use that proportion. We can say that the proportion is 0.7 with a margin of error of 0.13. So that's why I want to emphasize, well, why isn't it 0.13 or 0.12? Because those are actually closer to the margin of error, either incorrectly rounded as it is for answer B, or the last answer, that's the correct rounding of the margin of error. Now, what's the margin of error, you might want to know? Margin of error, in essence, is, let's see if we even asked that question. Oh, look at this. Here I'm being a little silly. You can actually use the round function. I haven't addressed it too much in this semester, mostly because we've switched to multiple choice, which has gotten rid of a lot of headaches for students. But I do want to highlight this because I think it shows how relatively easy it is to get the answer using R. In essence, with the round function, you can take the whole mess here. So ignore this. You can take whatever number you want here that I'm highlighting. You take the comma, and then you take the number of decimal points that you want rounded to. And in this case, you have the number 2. And you can round to 2 decimal places, any number, as long as you do that. Just a nice little convenience shorthand, not necessary for the class, but if you're using RStudio, you can estimate it this way. And I think some of these homework assignments will show that, but not required. Okay. So let's go down. I want to move a little more quickly. I'm noticing that I'm halfway through this section and I want to get more quickly than I've been going. I think in this section, I'll try to address the first 2 parts, part 1 and part 2, primarily because the third part that deals with differences in proportions, some of the aspects of interpretation of the R code and the data set were addressed in the previous section and are answerable using the code. That being said, if there are any concepts there that you want to address further, such as I've done with the last problem, feel free to let me know. Otherwise, I'm going to go in score order, as it were. So if we look at question 5, we're again asking for you to calculate the 95% confidence interval. Here, the logic is essentially the same, using the sample proportion p hat to calculate the standard error. So I'm not going to talk too much about the margin of error. Just keep in mind the margin of error is essentially 1.296 times the standard error. So the margin of error is essentially saying if we have a normal distribution, here I'm going to do some awful drawing here, but I'll show you what this margin of error is. So you have the standard normal distribution. Yeah, this is terrible. Oh, that's about as bad as the normal distribution can look. Just try to make that, use your imagination, folks. Okay, there's my point estimate p hat. It's like Khan Academy on steroids. The margin of error is the distance, is your standard error multiplied by some scalar. In this case, the scalar is going to be safely assumed to be 1.96 or basically 2. So standard error times, I can type this out even, 2, we can say 2, approximately 2 in expectation. Okay, I'm going to delete that because that's way too ugly. The main point is that 95% confidence interval is used more often, but you might hear this term margin of error quite a bit. In fact, I've heard it just even today colloquially. Someone was referring to margins of error, referring to, I think, an individual. I think it was on some internet message board, I think having to do with the new Star Wars game. If you know any of the stuff about that. But basically, what's the problem here? Well, margin of error is a term that you might hear quite often. That might refer to uncertainties in any kind of individual estimate, but in application, you're probably going to hear it mostly in terms of statistically, you want to make sure that margin of error is applied correctly. And you'll probably see it most often in public opinion polls, like political polls. You'll hear like, our true population proportion of the presidential approval rating, for example, is estimated with the following margin of error, plus or minus, then some percentage points. I think that's probably the most common you're going to see. especially with approval ratings having sort of the currency that they still hold, especially in public discourse. You'll hear this margin of error issue quite a bit. And just keep in mind it's 1.29 times the standard error. You can really impress people that way. And then you can say, well, I'm not so interested in what the margin of error is. Maybe you can use that margin of error. You can even take a look at some of the public opinion polls, and you can just remember, well, from that margin of error, it's actually a little bit of a convenience function, because I'll tell you what I do. When I look at the public opinion polls and I see the p hat, say we have the presidential opinion poll of 38% or 35%, wherever the President Trump, for example, is estimated to be, you will have his p hat to be 0.36. And then when you look at the research reports, you might see this margin of error estimate to be, I don't know, you could say 5%. I'm not sure what it is, 0.05. Well, that's very useful for us to know, because that basically tells us on average how much does that, say, would that point estimate vary? And that'll basically tell us it'll give us a really good idea of the uncertainty or the certainty of the estimate. So, that's something really crucial to look at. And keep in mind the margin of error here then, well, if it's basically what defines the distance between our p hat and our 95% confidence interval, then all we have to do to find the lower bound using the margin of error and just p hat, we can take our point estimate minus the margin of error, and that'll equal the lower bound of our 95% confidence interval. And then, of course, you just take that point estimate and then add our margin of error, and that'll be equal to the upper bound. And those are two important distinctions. I don't think we really emphasize too much in this class the margin of error, but you will see it a lot in polls. You'll probably see it in other sort of public opinion polls. You'll hear other people talk about it. And don't be surprised, I would say, if you see the margin of error referenced in the class, especially in the final exam. So the point I want to make here is, well, you might see some homework assignments that actually give you, say, the margin of error and ask you to estimate the 95% confidence interval. And you should know, well, with just the margin of error and the p hat, you will be able to estimate the 95% confidence interval. Okay, that's all I really want to say about margin of error as it pertains to 95% confidence intervals. Whether or not it addresses any particular questions, I think it's important for you to know for the final exam. Okay. See, I just ate up more time, but I think it's useful to know that distinction, because I think some of the homework assignments, we could have asked several questions for each one of these problems. So for question 6, we prompt you using what you know from question 5, what is the standard error? Okay, well, keep in mind you might also be asked to estimate the margin of error using just the standard error. Just remember that the standard error is 1.96 times the standard error, so it's basically double the standard error. But you might want to be a little more careful if you want to have a rounded estimate to 2 decimal places. I show basically that using the p hat again and multiply it by its inverse, and then divide it by the sample size, and taking that square root. Then you have, and then you round that square root to 2 decimal places. That's how you get your standard error. On question 7, we essentially change the parameters, or I want to use the parameter. I want to use the word parameter correctly here. Whenever we talk about parameters and statistics, just make sure that we really want to be careful that we're using the word correctly, the right word. In this case, the right word is going to be parameter when we talk about populations. Otherwise, we don't want to use the word parameter to be a little confusing. But what I did want to say was that we can change the sample size, we can change the p hats, and we can still ask you the same question, but keep in mind you're going to use the same question. You're just going to plug and chug a different sample size here to estimate the confidence interval. And I don't know if there's anything else that's warranted here to emphasize, except that, okay, for this 95% confidence interval, just use that same equation that you used before and then change the sample size. For question 8, we want to know the standard error. Again, on your way to the answering question 5 about the standard 95% confidence interval, the standard error is what should be around 0.02. And the margin of error, here we see that question creeping up, is actually double the standard error. So it should be pretty easy. You could actually say for question 9, it's a little disingenuous. Using what you know from question 7, well, you could also use question 8 here. In fact, it's probably easier if you use question 8, as long as question 8 is correct. So what is the margin of error? It's doubling the standard error, essentially. Now, that being said, I want to make sure that you're going to multiply the standard error times 1.96, not by 2. But if you had to do an off-the-cuff estimate, napkin math, well, that'll work here, because you can see that our correct answer for question 8 is 0.02. We double that, we get 0.04. So I think my little disquisition on the margin of error was warranted, because you'll see that question definitely in the exam. Now, question 10, we ask you to express the answers in terms of null and alternative hypotheses. Now, some of this might look a little confusing. Keep in mind, you just have to remember that when we talk about null and alternative hypotheses about the proportion in the actual proportion, about the population proportion and the sample proportion, our null hypothesis is going to be P equal to our estimates, and P is not equal to that estimate for the alternative hypothesis. And our test of a hypothesis in a one sample hypothesis test of a true population proportion is going to be driven by what we think the true population parameter to be. So just keep in mind, all you're going to do is switch out what that true population proportion might be. So don't use, I think it might be a little confusing here, because say if you look at this first question, this first alternative, yeah, actually if P is less than 0.05, you do want to use the alternative hypothesis, you accept that, but don't confuse P as a p-value with P to signify proportion. And I think that's an important distinction that this question sort of brings up, which is, I'm going to drive it here, it was in the modules, but p-value is equal to a test statistic to evaluate the, you could say the long run probability, to evaluate, I would say to infer the true, I would say to test statistic, I'll just say p-value test statistic, P is a population parameter. That's all I'll do. Someone is asking, well, why not p hat is not 0.6? Because okay, so if you notice, someone is asking a really good question. Well, what, and this is, I think, part of the issue here, is why some of these might be a little difficult. Why isn't it, so I just said why is not this one right here, because here I'm distinguishing between p-value as a test statistic and P as a population parameter. That's what could be one reason why you click this first answer. Why isn't it this one right here? Is someone had just brought this up, really good, great question. Well, it's because of the way that we're framing this question, and this is important to emphasize. So let me make sure, let me see if I can explain this correctly, and let me know if you still want further clarification. The reason we want to frame our null and alternative hypotheses in reference to this unknowable but estimated true population parameter is because of 0.50, is because our interest is in knowing whether or not the true population parameter, that is P equals 0.05, so our 0.50, is we want to let me frame it this way. The reason we want to frame our hypotheses in reference to 0.50 is because we want to test our hypotheses in reference to this hypothesized proportion. In other words, we're not interested when we're testing hypotheses. We want to phrase and frame our questions. It's not about necessarily describing what's in our sample. So this is the difference between inductive and deductive research. Inductive research, right? So if you look at inductive research, these are data-driven. Inductive is data-driven research, right? So if you want to do an inductive research project, sure, we can talk about, what is the sample size, but here we're talking about deductive, which is actually hypothesis-driven. Two major differences, and because this is a deductive hypothesis test, we're going to go based on theory, and we want to test the hypothesis that our true population parameter is 0.50, or that it is not 0.50. And this is because this is what we believed before. So that's a really good question. Now, because we have a two-sided one-sample hypothesis test, I should say, so you want to say that this is a two-sided one-sample hypothesis test. So I talked about this earlier this week and with several students. What is the difference between a one-sided and a two-sided hypothesis test? Well, a two-sided hypothesis test tells us whether or not it is a certain value, and it can be rejected. It's non-directional. In other words, all we're interested in is whether or not the hypothesis is equal to what we think it to be or not. So is the true population parameter equal to this value, or is it not? Well, that's different than saying, is it greater than a certain value? In that which case, we're basically asserting that there's a direction, not that it's non-directional, right? Because here we can say, well, is it within our zone of estimates? Is it plausible? I think that it's a little confusing, but the main point I want to make here is simply that in all cases, when we ask you to frame your null and alternative hypotheses, keep in mind that we're asking you to frame our research in terms of as a deductive enterprise. In other words, it's in reference to theory or hypotheses. It's not in reference to the data. So we might have a given hypothesis, but we're not using the sample data to estimate this. So when I say data-driven, I'm actually referring to sample size or sample-driven here. You can have a data-driven hypothesis, right? You can say, well, based on prior research, we would expect this sample to behave this way. But that's really hypothesis-driven research. And they're very different than inductive data-driven research. And we really want to be careful to distinguish those two, because we don't want to make that, we don't want to actually engage in what is often termed pejoratively as p-hacking or data dredging or data snooping, which means that, okay, you're just going to find a statistically significant difference without reference to what the hypothesis is. You really want to make sure that you have a clear research question, you have a clear hypothesis before you look at the data. Otherwise, you're just going to end up with false positives as your outcome. So that's the main reason we want to really be careful about how we frame our research. Okay, I think that's the main point I want to make here, just emphasis on deductive and emphasis on, I want to flag for you to be careful in terms of framing the hypothesis test. Okay, we'll keep going. And let's see, we have about 15 minutes left. So here, I might kind of force us to split the difference here. I wanted to, let me see. I'm going to go to concepts. I want to go to the next section, actually, I think, because I think the rest of the stuff on Z statistics, you'll see some of the code here. I think that'll clarify it. I talked about standard errors. I talked about margin of errors. I talked about 95% confidence intervals. And I talked about the success failure condition. I think those are the main concepts we really want to learn. I think the answers here are just means to understand those concepts. And I want to make sure that I address all the concepts before we end today's session. Let's look at question. Oh, hold on for a second. Let's see. Let's look at question 13, actually. So question 13, we ask, you have a random sample of 150 adults, and you find that the sample proportion who agree that the planet is undergoing climate changes, p hat is equal to 0.70. You want to test the hypothesis is that the actual proportion of the population is p equals 0.65. What is your test statistic using the hypothesized population proportion of 0.65? Now, the reason I want to focus on this question is, well, what is it? How do you estimate the z test statistic? You might want to know here. Well, just keep in mind that first of all, you want to think about this in terms of what are the null and alternative hypotheses. The null hypothesis here is that p will equal to 0.65, and then the alternative is that it does not equal to 0.65. So keep in mind that this is basically the same as before, but so the z-test statistic, though, is just another way of phrasing or framing what the standard error is, which is equal to p naught, or p of 0, times 1 minus p of 0, divided by our n. And we take all this, and we basically take the square root of this. I'm using the square root function in R, but basically the intuition is essentially the same. You take something, multiply by something else, you divide it by the sample size. Should look pretty familiar. Now, what is P naught here? Well, P naught here is P naught here is going to be 0.65. So right. So P naught is the hypothesized population proportion. So we take 0.65, multiply it by 1 minus 0.65, so 0.65 times 0.35, divide that by 150, our sample size right here. Let me use the highlighter right here. And we take that and then we divide it by a sample size of 150, and then we get our standard error. And keep in mind, when we talk about z-test statistic equals z-test statistic is also equal to another way of expressing the standard error. And if you do everything correctly, you take 0.6, so it's that mess up there, right? 0.65 times 0.35 divided by 150, and you take that whole mess and you give it a square root. And you can do that, test it for yourselves. Tell me if I got this wrong, but I think we have it right here. You take the whole mess, you give it the square roots, and you should get something, and you can round it to 2 decimal places. You should have something in the ballpark of 0.128. And that is roughly equal to 0.28. 1.28 rather. So just to keep in mind that when we talk about the z-test statistic, using our hypothesized proportion to calculate the standard error, we're basically estimating the z-test statistic based on our, hold on for a second, I'm sorry. It's not equal to the standard error. Where it's so easy. Remember the z-test statistic is going to be our difference in two proportions divided by our standard error. That's what it was. I'm sorry. Keep in mind, when we talk about the logic of using the z-test statistic to proportions, all we're saying is, well, we want to figure out what is the difference between two estimates, and then how much do those estimates differ on average, right? So you just want to find out the distance between 0.65 and 0.7, 0.05, and then divided by our standard error. And knowing the standard error is going to be the hardest part of this. So in this case, I'm going to erase a lot of this, actually. I want to show you how we get to 1.28. 1.28 is found by taking the difference. So the standard error here is going to be bound 0.04. Or you could say 0.039. And that's what I found before, right? I showed you with that mess before. So, but the z-test statistic is going to be basically p hat minus p naught, our hypothesized test statistic, right? Our sample test statistic minus the hypothesis one, or any two critical points, right? Any two estimates, divided by the standard error of the sample, which is our best guess at what the population standard error is. And what I showed to you before, take the square root of p naught, right? P naught, and then times 1 minus p naught. Divide that by our n. Take that whole mess, and that will give us our standard error. But the main point here, the innovation here, which you didn't see in the earlier assignments, is, hold on for a second, sorry about that, is the z-test statistic. Basically, in this case, it's going to be 0.70 minus 0.065, 0.65. So it's the difference between p naught and p hat. I think I have a different order, but it doesn't really matter. The difference of two variables it doesn't matter their order. And then you divide that by the standard error, which is 0.04. So that should equal to roughly 1.28. So that's how you get the z-test statistic. That tells you that they don't really vary that much from each other, if you remember the z-test stat. Is there anything else I want to say except that, well, what do you do with that z-test statistic? If I can scroll down. Yeah, I showed quite a bit here, right? So you can sort of see the answer here, but I don't want to emphasize too much the R code, except just that the logic is still the same. And that's what we address in question 14. Well, from the standard normal distribution model, because we have z-scores here, we know that 95% of z-scores lie in the interval from negative 1.96 to positive 1.96. Using the standard normal distribution as a model for the sampling distribution, what do you include regarding climate change using an alpha of 0.05? Well, we know what our z-test statistic is. It's 1.28. And in this case, we fail to reject the null that the population proportion is 0.65 at the alpha equals 0.05 level. So assuming that the sampling distribution is centered around 0.65, it is relatively likely that we would have obtained a sample mean of 0.7 from random sampling variation. In other words, it's because 1.28 lies within that interval, right? So that basically tells us, well, 0.7 doesn't vary too much from 0.65. It's consistent with our data, and that it could have just arisen by chance. It's noise. It's no signal there. We really need more signal than noise. So if we had a z-test statistic that's greater than that, say a z-score of 4, positive 4, well, you can basically reject the null hypothesis because it falls outside of that 95% distribution. So thank you for answering the question. Thank you. A student had answered helped me out with some of the calculations. So from basically what we know from proportions, this as we go through the homework assignment, we're only halfway there. You can see that, okay, we ask you to estimate the 95% confidence interval. It's the same method. And you can see that the math here using the round function that I talked about a little bit earlier. But I think if you look at the description here, this pretty much explains the answer. A two-sided hypothesis test and confidence interval based on the same alpha lead to similar results. A null hypothesis with an interval implies that we fail to reject the null. That is, these results are consistent with the null hypothesis. That's essentially the interpretation of question 14 answered in question 15. So we sort of hid both answers for question 14 and 15 there. One sample test and proportions in R, we did sort of address that in the homework assignments. I don't think there's too much I want to talk about because I did address quite a few of these questions, but I just want to end on the two sample tests, comparing groups in R, because we started with that. I want to end with that. You'll see that for question 25, for example, the first question in part 3, we ask you to compare the proportion of men and women. I just want to let you know that you don't have to have an exact rounded answer if you write them in, but it should be relatively close. You should not get an incorrect answer if it's within rounding error, just to let you know. If you do, please raise a fuss. But I want to end on this point that when we talk about a difference in two groups, when we look at means, is essentially the same logically when we compare the difference in two proportions. In this case, our hypotheses are going to be framed in terms of whether or not the difference in those means is equal to 0 or not, right? So here, if we look at the proportion in the sample who believe a certain field is scientific between men and women, we want to compare male and females' attitudes. Our null hypothesis is there's going to be no difference between men and women in attitudes, whereas our alternative hypothesis is that there is a difference greater than 0 or less than 0. And the main point here is that when we talk about point estimates for proportions and we're looking at groups, our point estimate for the estimate or for the difference between two groups is just that. It is our first proportion divided by our second proportion. And the biggest hang-up that a lot of students will have in estimating in finding the point estimate for a difference in two proportions, or a difference in two means, I should say, is ensuring that we're keeping intact the order of these categories, because the difference in two groups makes sense only as long as we keep each reference category the same. So if we take, say, assuming that, say, the differences of the point estimates between male and female is going to be positive, we want to make sure our null and alternative hypotheses are framed in terms of a positive difference. Say, let's imagine P female is equal to 0.7 and P male is equal to 0.5, although I know they're different in the homework assignments. Well, then our point estimate would actually be equal to, what would it be equal to? It'd be equal to 0.2, in which case our point estimate is actually a positive value. So just make sure that you can find our point estimates using a difference in two proportions. Otherwise, I think sections 2 and 3 are more covered in the homework assignment, but if you have, in the R code, but if you have any questions regarding those aspects, please let me know. Now, to give you an aperçu for next week, we're going to focus more on categorical data for this upcoming homework assignment. So, and then after that, we're going to go to analysis of variance, and then we're going to revisit simple linear regression and infer simple linear regression using the logic of inference and hypothesis testing, so that we can use regression in a sample. So thank you very much. If you have any questions, please let me know or let the other teaching staff know. And I hope you have a great rest of the week.